Good afternoon, Year 12 higher level chemists. You may remember in the last screencast video, we were looking at Unit 2.1, changing concentrations of reactants and how that affects rates of reactions. Now, on the Firefly page, you may recall we were working our way through a PowerPoint. I'm going to scroll down past the simple concepts one, down to this one, reaction mechanisms and rate laws. Now, in the last screencast video that I made for you, we were focusing upon rate laws. And I said that we would leave mechanisms and how these two relate to one another till this one. So that's what we're looking at in this video. So I'm going to pick up from, it's approximately slide number 16, I think it was, in this video, which I'm going to open up in a separate screen here, which is, page 15 was the where we'd got up to, in fact. So in the last video, we'd seen that for any chemical reaction, such as the reaction between reactants A and X, we can write a rate equation which describes the relationship between the rate of the reaction and the concentrations of those two reactants. There may be more than two in some cases. The key thing here was these numbers that we need to raise the powers of the concentration to in order to define that relationship. These numbers, you may remember, were called the orders of reaction with respect to each reactant. So this one is 1, that's first order with respect to the concentration of A, and 0 order with respect to the concentration of X. So they behave differently. 0 order, if we raise this one to the power of 0, that just reduces to 1. So this is rate multiplied by this expression times 1. So we can actually just omit that from the rate equation. So it reduces down to this in this particular case. And what that means is the rate of reaction is only dependent upon the concentration of one reactant, which is unexpected, perhaps, if you've just completed a GCSE recently, where we would generally say that a rate of a chemical reaction is proportional to the concentration of reactants. As concentration goes up, rate of reaction goes up. So this does seem a little bit contradictory from what we've met already. Let's dig deeper though. Notice it only applies to one of the reactants, not the other. Now, the reason for this is something to do with the mechanism by which this particular reaction takes place. Now, I put this as a cautionary note in the last screencast, the fact that we can only establish these rate equations by looking at experimental data or experimental evidence. You can only find a rate equation by doing some reactions. You can't predict the expression for the rate equation by just looking at the balanced chemical equation. You've got to know something about what's going on during the course of the reaction. So, the balanced equation, A reacting with X in a 1-to-1 ratio, giving a product AX. Apparently, based on experimental data, the rate equation shows that the concentration of X has no effect on the rate of reaction. Now, this next slide, I'm going to skip over that for now. We're going to come back to that. It'll make more sense, I think, once we've looked at the illustration rather than the description of it. So this is the reaction that we've just met. It's the reaction between A and X, whatever they might be, two reactants to produce a single product. They react in a 1-to-1 ratio. Now, we've already established what the rate equation is and seen that it excludes X. Why? Let's just break it down. Now, this particular chemical reaction, this theoretical chemical reaction here takes place in 2 steps. The first step only involves reactant A. And this one, look at the fact there's 2 steps here. This one is, we describe this one as being the slow step. So in the first step of this particular reaction, reactant A is slowly reacting to produce something else. They've just represented here as a sort of an A with a halo thing on it. Let's call it an intermediate substance. It's not a reactant, it's not a product. So in the first step, A slowly transforms into something else. Okay? In the second step of the conversion to products, X is now involved. X now reacts with this intermediate substance, but this happens fast. To all intents and purposes, it occurs immediately. So in other words, as soon as this intermediate appears in step one, it immediately reacts with one of the X's to make the final product. Now, what else can we say at this stage about this? Well, we've got two steps in the mechanism. The first step is slow in comparison with the second step. The slow step is the one which overall controls the rate at which product is going to form, because A is slowly making this intermediate, which then immediately reacts to make product. So what controls the rate of product formation is how quickly this thing appears. And that's the slow step. So we call the slow step the rate determining step. And here we're referring to the overall rate of the reaction, the overall rate of this reaction here. This slow process is the one that controls how quickly the whole thing can happen. That's why it's called the rate determining step. Now, some of the other vocab that you can see floating around in here, step one of this two-step mechanism is described as unimolecular, quite simply because there's only one particle, only one molecule reacting in that step. So it's unimolecular, molecularity 1. Step 2, on the other hand, there are two particles or two molecules or two species reacting together in this step. In this case, it's whatever X is, a molecule and this intermediate substance. So there's two particles reacting. This is described as bimolecular, molecularity 2. Now, if we were to look at the net effect of these two separate steps, A reacting to make an intermediate, and then B, X reacts with the intermediate, so that then disappears, and we get the final product. Now, you've seen before how we can combine two equations together. If we add these two equations together, everything on the left of the arrows goes on the left of one equation, everything on the right of the arrows goes on the right of one equation, and we can omit anything which appears on both sides of the equations because it's not a reactant, it's not a product, it appears and then it disappears. We're left simply with A plus X gives AX. So the net effect of this mechanism corresponds to what we can see up here. Now, I'm just going to scroll back a second. Some of the terms we've seen here. What I've been referring to as a mechanism is the steps that occur during the conversion of reactants to products. Here it says each step is called an elementary process. I'm not sure that you necessarily need to define this, but just to see that they are discrete processes that occur one after the other, I think is enough for that. This last point is what I was describing, in that if you combine those two steps, the two mechanism steps, you should get the overall equation. Or in the case, sometimes you'll see up to 3 steps or maybe more. But if you add up and combine all of those mechanistic steps, you should always end up with the correct balanced overall equation. That's what it's talking about in this last one here. Okay. Let's just move down a little bit further then in this. Now, I mentioned the idea of the slowest step being the rate determining step, and I'm not going to dwell on this slide or the next one. This is just, if you need it, this is just to help you to sort of try to understand why the slow step is going to control the overall rate of conversion from reactants to products. I'm going to pause, or suggest that you pause the video just for a second, look at this diagram for a few moments, and see if you can think for yourselves how that illustration of traffic merging and popping out via the other side of a toll bridge could possibly help to understand what's going on in terms of this equation. Please pause the video for a moment, have a think. Okay, welcome back. Did you have a think? Now, I think the idea, hopefully you've got this for yourselves, is, for example, this stream of traffic could be reactants A's, and this stream of traffic could be reactant X's. And what's going to pop out the other side of the toll bridge down here is going to be product AX. What's ultimately going to control the rate at which AX products pop out the other side here is going to be whatever's the slowest process going on up here. It might be that traffic stream A passing through here could be very slow. There might be a slow ticket operator down here, whereas passing through toll booth X might be actually a very swift process, so they can move through quite quickly. But the A one is quite slow, so it doesn't matter how much traffic there is in the queue for X, the fast-moving one here. If we're limited by how quickly an A can pop through the other side, then that's going to control how quickly we make AXs. So ever so slowly, an A will pop through and there will immediately be an X to react with it, and so you'll get a product. It's a bit of an abstract way of looking at it, but that's what that is. You'll see it in the PowerPoint yourselves when you're looking through. So I'm going to move forwards a little bit in the PowerPoint at this stage, down to here. And we can perhaps go back to some of those written descriptions later on. Let's just look at the examples of these things and how they work, first of all. So this is a sort of a general form. We can write this for any type of chemical reaction. A few things to note about it. Now, this is another generalized reaction. This is not A and X anymore. This is the reaction between an A and two Bs to make a single product, which is an AB2, a bit like an H2O, something like that perhaps. Okay, for this one, we've not been told what the orders are for the reactants. It's just saying that they have an order. Rate of reaction with respect to reactant A, M is the order for that one, and rate of reaction with respect to the concentration of reactant B, we don't know what it is, we just give it a letter N, whatever that is. So N is the order with respect to B. It could be 0, 1, 2, perhaps. So the overall rate equation would look like this. Now we can write this structure of rate equation for any chemical reaction that you're given, but we won't necessarily know what the values of M and N are unless we've got experimental data. The values of M and N do not correspond to these coefficients in the balanced equation. The values of M and N are what we get by doing experiments only, so just please be careful of that. Okay. Another thing just to note then is the overall order of reaction is just the sum of these molecularities here. So M plus N is the overall order. Okay. Now, sticking with the AB job. Now, if we did have some data on this particular experiment, suppose people had done some investigations and they'd found that the rate equation looked like this for this particular reaction. In other words, a rate of reaction is directly proportional to the concentration of reactant A. And if there's no number there, that just means 1, remember? So this is first order with respect to A, and the rate of reaction is also directly proportional to concentration of reactant B. And again, there's no little number written up here. There's no 0, 1, or 2. If there's no number, that means it's a 1 implicitly, because concentration of B to the power of 1 is the concentration of B. So this is first order with respect to each of the two reactants. So 1, 1, to reinforce not the same as these coefficients in the balanced equation, which are 1 and 2. Okay, now why is that the rate equation? Why is it first order with respect to each of those two reactants? To answer that question and to understand why, we need to look at the sequence of steps that are involved in the conversion of reactant to product. Okay, Now, this is a suggestion, a hypothetical suggestion here, what might be going on, and you'll sometimes see exam questions of this nature. Okay, so we could suggest that maybe step one is a slow step, and it involves reactant A and B reacting together slowly to make some sort of a intermediate, AB, with air commas either side of it. Why might we suggest that is a first step, and why might we suggest it's a slow step? Now, this is an important idea to pick up on. When things are to the power of 1 in the rate equation, A to the 1, B to the 1, it rather implies that there is one particle of A reacting with one particle of B in the slow step, or involved in a step that occurs just before the slow step, if there's several steps going on. But for simplicity here, let's say A to the 1, B to the 1, that means there's one of each involved in the slow step. So we could propose that step 1 is bimolecular, 1A and 1B are slowly making this intermediate. Now, that's clearly not the product, so we're going to need another step. So we could then suggest, looking up here, we actually ought to be using 2 Bs. We've only used 1 so far. So we might then say in the second step, let's have a B getting involved, and the B has to react with the intermediate because that's got to get used up and disappear. So you might then propose a second step, which is B reacts with the intermediate. This we're suggesting is quick because the other one was the slow rate determining step. And we could propose here B, A, B. We can actually suggest that we would get what is the final product, AB2, which we can see up here. So what we've done, we've utilized the idea of orders to see the ratios, the amounts of reactants in the slow step. We've also thought about the fact that, well, we need 2 Bs in total to react, so we've used a second B in a second step. And now let's just check if we were to combine these 2 mechanistic steps, if we combine those and cancel things out, does it match the overall equation? Well, we can strike out the intermediate because it appears and then it disappears. It's on both sides, we can cancel that out. And over on the left then, we've got 1A and 2 Bs. And on the right, we have an AB2. So the net effect is this, which is what we were after up here. So that actually works very well. Okay. Now the next slide, when you look at that one, it's just the same thing, but rather than writing it as formulae, it's showing it as particles involved, like we did for the AX one right at the start. Okay, so this particular reaction is second order overall. Now, I think at this stage I'm going to pause. You can explore some of the further slides yourself. You can go back to the text, the written descriptions that appeared earlier on that I skipped over because I have utilized these ideas in the explanation of what we were doing when we suggested a mechanism that matched the overall balanced equation based on the experimental data. Okay, so I hope that helps for now to get you started. I'm sure I'll be giving you a bit more support shortly, but I'm going to pause that one for now. If you've got any questions, you know how to contact me, please feel to drop me a line and I'll give you a bit of further help. Okay, stay well, folks. Thank you.